All right, so what we're covering here, functions and what their graphs will look like. So that's what we're getting started on here. A function is a relation, basically, and a relation is any set of ordered pairs. And we've been talking about ordered pairs where you have an input, essentially, and then an output. And so the following represents a relation between and its top speed in miles per hour. And so what we have is cheetah is 70, human 28, lion 50, and tiger 49. We have two things that we can talk about this. First off is the domain. That is all of the inputs that you can add for this, all your inputs. That's going to be things like cheetah, human, lion, and tiger. Those are all of our inputs. All right, and so what we have here is cheetah, human, lion, and tiger. And then we have our range, which is essentially all of our outputs, which is the things that correspond to them. You say cheetah and the output is 70. Human, 28. Lion, 50. Tiger, 49. And so then that's what we end up getting there for all of our relations. And then what we can do is say, well, we don't just have relations, but we also have specific relations that are functions. And for it to be a specific function, the relationship has to meet a certain set of requirements. Okay, and this requirement is that in order for a relation to be a function, the idea is that for every single input, you have just one corresponding output. So each input, or X, you have it corresponding to a single output, which will be your Y value of your ordered pairs. So notice cheetah only goes to 70. It doesn't go to 70 and 50 or something like that. For cheetah, it's the only one. It just has 70 like that. There's no repetition of the inputs. They don't, each one of them only gives you one output. In fact, giving you that output is called mapping to. You can say cheetah maps to 70. Or human maps to 28. Lion maps to 50. You give it an input and then it maps it over to your output. So let's take a quick look here at some of each of these here. And I'll do this first one and then I'm going to want you to decide on the other ones here. So the first one is determine whether each relation is a function. So we look here and we see cheetah goes to 70, human goes to 28, lion goes to 50, and tiger goes to 49. This is most definitely a function because each of these inputs only has one arrow pointing to an output. All right. Conversely, if you look at the second one, this is not a function. All right, not a function. And that's because this input here of New York actually is mapping to two different things. It's mapping to the Yankees and to the Mets. All right, so it's mapping to two different things. Even though it almost looks like it's pointing to the Cardinals, it's mapping to the Mets and Yankees. So it's not a function. This number 3 here, this one actually is a function. Even though we have two different inputs going to that 7 and mapping to that -7. That's okay. That's acceptable because each one of them still has its only one output. So the outputs can repeat, but the inputs cannot. And that's what you're looking for here. So here, this, that's okay. That's okay. This up here, that's not okay. Okay, that's not a function. All right, and then here, look at this last one. Here you see 2 goes to 9, 5 goes to 8, and 19 goes to 9. That means each one only maps to one output, and therefore this is a function. All right, so go ahead and take a look at this next little section here, 5 and 6, and try determining whether each function is a relation, and then if so, put it down as what its domain and what its range is. All right, here we're going to talk about function notation. And here what we have is a function is a special type of equation. So it's going to have an equal sign, right? Equation equal. Therefore, it is given a special name. And typically that special name is a letter. So it's like a special letter to denote it. And that's going to typically be lowercase f, lowercase g, and lowercase h's is what we usually use to describe functions. All right, so f, g, and h. Some examples you might be used to is something like f of x equals 2x plus 1. You may have seen this before as something like y equals 2x plus 1, but that is a function. You might also have g of x equals x squared plus 5x plus 22. That could be a function. And then another one, h of x equals the log of x. That is also a function. Log functions are functions. Over here, we have a nice little picture. I really like this one because I usually end up drawing this picture, but thankfully it was added here, or at least not as detailed a version of it. But essentially, this is the way I think of functions. I think of them as essentially a machine. So this machine here, this is the function. All right, it's our function machine. We have an input, and then we have an output. All right, you input things that are in your domain. So you input your domain, and then it'll output stuff that's in your range. Okay, and it just does some work on it, and it gives you something back. You could even think of this like if I took, say I had a function, I had a machine that made breakfast, right? If I gave it, I don't know, if I gave it, or it made food or something, and if I gave it something like, if I gave it some eggs and some bread or something, it would make me like an egg sandwich if I throw them in there. And so it'd be a function if every time I gave it eggs and bread, it only gave me like an egg sandwich. But it's not a function if, say, I come along and I give it, you know, cake mix or something like that, and suddenly it outputs a cake, or it could output some sort of cupcakes or something like that, something different. And then in which case it's no longer a function. So we're really just interested in this idea of thinking of functions as it's some sort of machine that does something where we give it an input and then we look at the output that comes up. This kind of thinking will actually be very helpful later when we start combining functions together, where we send one function into another function. But essentially, you give it an input, you let it do its work on it, or you do the work on it for the machine. You figure out what the machine would do to it, and then you get an output. And some examples of that are also just right here. And the way we indicate our input is by putting it right there inside the parentheses of our notation. So this is read f of x equals x squared minus 2x plus 3. And so then what it's asking us to do is to evaluate each of the following. So this one was f of x. This one right here is f of 3. Like that's the way you would say that one. And what it's doing is telling us, instead of just putting an x in there as a variable, we're going to go ahead and plug in 3. So it's telling us, this part right here is telling us x equals 3 is what we're trying to do. So if we do f of 3, then we go everywhere there's an x and we put a 3 in. I highly recommend you always put parentheses around it when you're plugging it in. This will help a lot when you're dealing with negative values and help you keep them straight so you don't make a sign mistake and miss something. And then minus 2 times that 3 again, and then just plus 3. And then you would just go through and start figuring this out. 3 squared is 9, 2 times 3 is 6, and then plus a 3. So 9 minus 6 is 3, and 3 plus 3 is 6. And there's your answer for f of 3. F of 3 will equal 6. All right, so what I'm going to go ahead and do here is pause for a minute, let y'all try working on these other ones here, and see how they go for you. All right, so here what we're going to do is take a look at graphing these functions, and we're going to try graphing two slightly different functions on the same coordinate plane, and then we're going to look and try and describe how the two graphs are related to each other. So the first graph we're going to do is f of x equals x squared. That's this one right here. I'll do it in purple. And we're going to do this just by plugging a few numbers in. And we know this kind of shape is one of those U-shaped graphs called a parabola. So we're just going to try plugging in a few numbers, -1, 0, and 1, and see what we get. So this becomes f of -1, which is just -1 squared, which is just 1. And so my ordered pair is -1, 1. If we plug in 0, it's f of 0, which equals 0 squared, which is just 0. So the ordered pair is 0, 0 is one of my solutions there. And then I can try plugging in 1. F of 1 is equal to 1 squared, which is just 1. And so this is the point 1, 1. If I go over here to my graph, I can plot these 3 points. I have the point -1, 1, the point 0, 0, and the point 1, 1 right there. And that gives me those 3 points, and then this makes a kind of U-shaped graph we call a parabola, and it's going to look like this. I think I can do this other side a little better. So something like that. Okay, and now let's take a look at the x squared plus 2 graph, which I will do here in red. And we'll plug in the same points, -1, 0, and 1. See what we get. So this becomes g of -1, which is -1 squared and then plus 2. -1 squared is 1, and plus 2 equals a 3. So we have the coordinate -1, 3. If we plug in 0, we're doing g of 0. This becomes 0 squared plus 2. 0 squared is 0, plus 2 is just a 2. So the ordered pair 0, 2 is what we get there. And then the last one here, we can do g of 1, which is 1 squared plus 2. 1 squared is 1, plus 2 is just a 3. So we have the coordinate 1, 3 there. If we put all of these on here, we have the point -1, 3. So that's right there. We have the point 0, 2. That's right there. And we have the point 1, 3, which is right there. I then can draw in this U shape here, and we end up with something like this right there. And if we look at this carefully, what we can see is these are actually the same graph. It's just that what's happening is because we have this plus 2 on each of them, we're just adding on 2 to every point. Every point is just shifting up by that 2 despite my bad drawing. And that's what that plus 2 is doing. So what we end up with is we end up with a graph that's shifted or translated. All right, those are the same thing. It's shifted or translated up to. Shifted up to, translated up by 2. All right? And that's pretty much it for what, our introduction to starting to just kind of do things to move graphs around. On the next page, we have what is called the vertical line test. And I'll do this real quick before I see if there's any questions. And this is essentially just a way to look at the graph of a function and try to determine if it is a function or not. So if any vertical line intersects a graph in more than one point, the graph does not define a function. So what you want to do is go through, look at your graph, and just see, is there anywhere I can draw a vertical line that's going to hit my graph more than once? So if we look at this one, and you can draw it anywhere you want. I draw that one in, do it with this tool here. I'll draw this one in. Nope, it only hits it once. Nope, it only hits it once. Nope, it only hits it once. Anywhere I try to draw a vertical line, it's only going to hit the graph in one point. Therefore, yes, that one is a function. If we look over here at number 14, on the other hand, anywhere I try to draw a vertical line, like here, it doesn't hit it at all, that's fine. It can not hit it, and that's acceptable. But if I come over here and I draw this vertical line in, we look at this, I've hit it in 2 places, here and here. Since I hit the graph in 2 places, this is not a function. All right, and it doesn't have to, you only need just one location on the graph where a vertical line hits it twice, and it's all of a sudden it's not a function. All right, you don't have to have multiple places. This one has multiple places. All of these places it's going to hit it twice. Any one of those says, all right, not a function. All right, so I want you to take a look at 13 and 15 and see if you can determine if they are functions or not based on the vertical line test. All right, let's go ahead and try and do this one here, where we're going to find some different information just by looking at the graph. So first off, we're going to look for the x-intercepts, if there are any. We can find those. I'll do them in green. Remember, this is anywhere it crosses this x-axis right there, that horizontal x-axis, and that's going to be in 2 places, here and here. And so we just need to write down what the x value is at those locations. And the first one is at x equals -1, so -1. And the other one is at 1, 2, 3, x equals 3. And so our x-intercepts are -1 and 3. The y-intercepts occur whenever it crosses this vertical axis here, right there. And we see that it crosses that axis right there in 1 point. And the y value there is just -2. 1, 2 down from it. All right, those are our x and y intercepts. Next, it's asking us to find specific values. Here, f of 1. This is us figuring out when x equals 1, what is our output value? And so we do that, we go to x equals 1, that's right here. So we go to x equals 1, and then we have to figure out where or what the output value is. So we then go to where we hit the graph, which is right there, and then we read off the y value, which is right there at -4. So at x equals 1, y is going to be -4. That's what that ordered pair is right there. That's the ordered pair 1, -4. All right, that's the coordinates of that point. Okay, taking a look at the next one here, we have f of 0. That's going to be plugging in, again, x equals 0. And so when x equals 0, we're starting right here in the center at the origin, and we're just going to go down and see, all right, our value right there is -2. So this is -2. Okay, so we got that value. The next one is f of x equals -1, or not f of x equals negative, f of -1. That's when x equals -1. And so we're going to go over here to x is -1. That's right there. That's also right where we're hitting, right where the graph line is. And so it's right there, y equals 0. All right, so those ones we found pretty quickly. The next one asks for what value or values of x, is f of x equal to 4? So what we're going to do here is we're actually going to go to where the y value. So this is the x value, this is the y value, right? This is our output. So we want to know what input values give us an output of 4. All right, so we come up here to y equals 4, that's right up here, and we look side to side. And we see that we are actually going to have 2 x values that will give us y equals 4. The first one occurs right here at x equals -1, -2, -3. So x equals -3 is one of them. And then the other one occurs over here, we drop down at x equals 5. So if we input -3 or we input 5, we will get an output of 4, which is acceptable to have the same output for 2 different inputs. That's allowed for functions. So put in -3, you'll get 5, or you'll get 4, put in 5, and you'll also get 4 as your output. Okay, next, the function's domain. This is essentially all the numbers that we can possibly plug in. Well, if you look, we've got these arrows on the end here, and these arrows just keep pointing on forever, which means that this will go out and eventually get all the x values that we can. Therefore, our domain is all real numbers, or we can say it goes from -infinity to +infinity like that. That's our domain. We can plug in any x value we want. It'll take any number, any real number as an input. Now, the function's range, this is all of our outputs, right? So this one is our inputs, right? This is our outputs. Well, if you look here at our outputs, let me do that in, I guess orange I'll do. If we look here at our outputs, all right, they stop here. They don't go below y equals -4. That's the lowest one. When we start going up, they go up forever, but they don't cross below that line, the y equals -4. Therefore, our domain, or our range, is going to be inclusive of -4. It goes down to -4, and then it goes up to infinity, and we never include infinity. So we don't get anything below that -4. All right, so that's that one. What I'd like you to do is start working on this one and the ones on the next pages where you're doing the similar kind of things, and then checking your answer and seeing how you do.